So one of the best ways for us to visualize sets and to work with them is actually by using Venn diagrams. It's a very good way, very easy way for us to visualize the sets. And how does it work? Well, basically we have a rectangle and we're going to put all elements which are in our universal set in that rectangle. And we may also express our sets inside of that rectangle, usually using circles. So let's say that I've got a universal set of all numbers, so x, such that x is less or equal than 10, and x is, let's say that only positive integers, just so we can practice some of those notations. Okay, so this is positive integers. So if you had to express this in another way, just by drawing the elements, which would be the elements of the set? Well, since we're only taking the positive integers, 0 is not going to be in it, or will it? Nope. So 0 is not a strictly positive number. So 1, 2, 3, 4, all the way to 10. That would be our universal set. And then we could simply draw a rectangle, right? That's our universal set. And we have our numbers inside of it. 1, 2, 3, 4, 5, just lying there. 6, 7, 8, 9, and 10. Right? 10 is included because we have x less or equal than 10. Now what if I had another set? Let's say that I've got set S, which is 4, 5, 8, and 9. Right? So I could express the set in our Venn diagram just by drawing some set here. Pretend that it's a circle. It doesn't have to be a circle, but that would be my set S, 4, 5, 8, and 9. So all elements which are in my set should be inside of my, between quotes, circle. Alright? So a very simple example here. So we've got this universal set, which is 0, 1, 2, 3, 4, 5, 6, 7. So it's, well, all natural numbers, for instance, from 0 to 7. That could be it. And I've got this set, E, which is 2, 3, 5, and 7. Looks like prime numbers, doesn't it? Prime numbers inside of that set. List the set E prime and illustrate, the complement of E, and illustrate E and the complement of E on a Venn diagram. So that's fairly simple, isn't it? So the first thing that we would have to do is to draw our rectangle, right? So there's not much room to get it wrong here, right? So that's our rectangle universal set. And inside of that rectangle, we're going to put all numbers. However, let's already select a space for numbers which are in my set E. So inside of my set E, I've got 2, 3, 5, and 7. Now, which numbers do I have in my universal set which are not in set E? Well, what are the numbers which are here but not here? So I've taken 2, 3, 5, and 7. So what do I have left? Oh, 0, 1, 4, 6, and that's it. Do I have to worry where they are? No, because if you think about it, a 0 here or here, it doesn't matter. Now, this inside would be my set E, and those which are in the universal set but not inside of set E, they would be our complement of E. Alright? If you use different colors, you could just, for example, let's have our set E here, 2, 3, 5, and 7, and I could just pick a different color, 0, 1, 4, and 6, and those would be our complement of E. And all of those are inside of our universal set. Cool. So, letter A. What is the number of elements in set E? Well, how many elements do I have here? You don't even have to draw, you didn't even have to draw the diagrams for this one, right? You could just look at our sets here. So 1, 2, 3, 4 elements. But we could also look here. How many elements do I have inside of this circle? 4. So 4. Letter B. What is the number of elements in my complement of E? Well, 4 as well, right? And you could look at your universal set. What do you have left? 4. That's 4. And the last one, which is we've seen this before. What's the number of elements in the universal set? If you just counted 1, 2, 3, 4, 5, 6, 7, 8, you would have 8. However, whenever you know the number of elements in a set and its complement, if you add those, it should also give you the number of elements in the universal set, because those sets combined should give you the universal set nevertheless. Now in this case, I know it's obvious, but it's worth noticing that my set E should be a subset of my universal set, right? And complement of E as well, right? If I had another set, let's say that I've got set A, which is just, let's say, 3 and 5, then A would be a subset of E, right? And would also A would also be a subset of our universal set. Anything that we have here obviously will be a subset of the universal set, because the universal set is everything. So it's either going to be a proper subset or just a subset. All of those, they are proper subsets because they're just a portion of the set itself. Now, Venn diagrams also give us a very easy way to visualize how our special sets interact with one another. So if you remember what we have covered before on our special sets, our special number sets, we've got the natural numbers, the integer numbers, the rational numbers, and the real numbers. So natural numbers, what are the natural numbers? Basically numbers that you can count: 0, 1, 2, 3, and goes on to infinity, positive infinity. What are your integer numbers? So it's all natural numbers, but considering its negatives as well. So plus 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on, up to plus or minus infinity. What about your rational numbers? Well, rational numbers, they are numbers which can be written as a fraction a over b, right? But a and b, a is a integer and b is a integer, right? So this is rational numbers, and the real numbers, they are everything else, right? So here we are going to have all decimal numbers, all fractions, recurring numbers, right? All surds, pi, anything that you cannot write as a fraction. So if we observe the way that the sets are organized here, we can see here in the middle the natural numbers: 0, 1, 2, 3, 4, 10, 20. I'm skipping some numbers, but all the numbers in between here, like 15, 16, all numbers, whole positive numbers, should be inside of this, right, which is your natural set. Now, covering, right, outside and actually engulfing all the natural numbers. So we've got the integer numbers. So all natural numbers, they are integer numbers. But we've got some more numbers, which are the negatives. So any number that we have here inside, any natural number, on our integer set will also have the negatives. So -1, -2, -3, -4, -10, -20, just to put the examples here that I've shown you, right? So all the numbers which are in here, they will be on the natural numbers, they will be also on the integer numbers, but negative. So we can say it's fairly simple to see that the natural number is actually a subset, a proper subset of our integer number. And likewise, since you can always write any of the numbers, for example, if you take any number, any natural or integer number, like 2. 2 is a natural number. I can write it as 2 over 1, right? 2 is an integer and 1 is an integer. They are natural, but they are also integers. So I can write it as a over b. So that's also a rational number. So any number, for example, let's say -4. -4 can also be written as -4 over 1. So that's also a rational number. So any number which is in between, natural or integer, can also be written as a ratio, so it's also a rational number. So we can easily see that all integers, they are a subset of our rational numbers. And obviously the natural numbers, they are also a subset of our rational numbers. All proper subsets, because the rational numbers, they will have much more than just what the integers or natural numbers have to offer. And last but not least, so we have all numbers here, like recurring numbers, which we know the pattern. So here it's 0.3333 because we can write this as 1 over 3. So we can write this as a fraction. This is a mixed number. We can write this as a fraction as well. 5 we can multiply by 4, so this would be negative 24 over 4, right? 0.2 can be written as 2 over 10. So all those numbers, they may be written as a fraction, even though they are not, but they may. So if you have, let's say, square root of something that you can solve, and you get a fraction, it would be here. If you can solve it to a whole number, then it would be here. If it's a, well, root, always positive number, so it would be natural. Now, if you notice here your your real numbers, roots of 8 is a surd, that's 2 roots of 2, and you cannot solve this roots of 2. It's going to be a number that never ends. Roots of 5 here is also a surd. Root of 2 here again, right? Numbers that never end, so there's no pattern here. We could also have pi, right? There are other numbers as well that we could take into consideration, other constants. Here, so 0, 1, 0, 0, 1, 0, 0, 1. So this is a number. You can see that the zeros are increasing, but, well, there's no way to write that as a fraction. And there you go. So all real numbers. So integer, natural, or rational numbers, they are all proper subsets of your real numbers. So basically the real numbers, they're going to contain everything which is inside of those sets. So it's a good way to use Venn diagrams to visualize those special number sets. So let's take a look at one example here. I've got some numbers and I would like to illustrate them on a Venn diagram. So using our special number sets. So we've got root of 3, 8.5, -2, 7.1, 16, and 0.115. So first thing, let's just draw some sets. Now, as I told you before, there will be times when those will not be circles, right? And there you go. Oops. Awful sets, but they will suffice. So the one on the outside is, so everything's a real number, so that's our universal set. Here we've got our rational numbers, here we've got the integers. They are representing those, okay, which are the ones inside. You don't have to draw arrows, I'm just showing you. And these would be the natural numbers. So let's take a look at each one of them. So roots of 3. You can always pause the video and try to do it yourself. Now, roots of 3 is a real number. Let me use a different color. So roots of 3 is a third. So you cannot simplify it. If you try, it's going to be a number that never ends. If you put that in your calculator, it's going to give you a number that never ends, and it will stop somewhere. But your calculator is just rounding the number, just like we've done before. It cannot show you everything, so it stops somewhere. It cannot be calculating numbers and showing you numbers forever. 8.5. Well, that's a number that's written as a fraction, so that's a rational number. 8.5. You can always write this number as 9 halves, right? Sorry, no, 17, right? 8 times 2, 16, so 17 halves. That's the same thing. Now, -2, well, integer numbers. 7.1, this is tricky because sometimes students think, oh, that's a real number. Well, I can write this number as 71/10. Right, just like this last one, 0.115, I can write this as 115/1000. So both of those numbers, they are rational numbers because they can be expressed as fractions. So 7.1 and 0.115. And those would be the equivalent fractions. They don't have to be a fraction. As long as they can be written as a fraction, that's fine. And the last one, 16. Well, positive and whole number, so that's a natural number, and there you go. So, we've got a universal set here. A different example now. So, our universal set is all integer numbers, right? So, we've got integer numbers here, and we're going from 0 to 12, including those numbers. So, since they are integer numbers, we're going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? I've got two subsets, so one is A, which is 2, 3, 5, 7, and 11. So that seems to be all prime numbers in that set. And I've got 1, 3, 6, 7, and 8, which, I don't know, just a set. Show A and B on a Venn diagram. So, let's do it. First thing you do, draw your rectangle. Oops. So draw a rectangle roughly. And let's draw, now we've got two sets and we can see that there are some things that they will have in common, right? So 3 is shared, 7 is shared, and that's all. So when we draw our sets, let me use a different color here. So let me first draw sets, which I'll call A. Alright, now set A, I'm going to have 1, 3, 6, 8, and 7. Oh, that's set B. I've just taken those numbers here and I've spread them on a circle here. Now we're going to have another set, which is our set A. I'm going to use a different color. So let's say this is our set A here. If I was just to draw a circle like this, now take a look, because I'm showing you something which is wrong, and then we're going to adjust it. If I were just putting A here, I would have 2, 3, 5, 7, and 11. But if you notice, look, I'm going to have 2 3s inside of my universal set. Aren't those the same thing? And 2 7s, aren't those the same thing as well? So those numbers, they're actually shared between those two sets. So we're going to do something slightly different. What we're going to do here, since we know that they have things in common, I would have to, and I'm going to undo this just for a minute, we would have to draw two overlapping sets. Alright, just make it a bit, there you go, now it's better. So A and B. Now let's spread all items, all elements that we have on set A. However, the ones which are in common, we're going to share. So 2 is not shared, 3 is shared, 5 is not shared, 7 is shared, 11 is not shared. Now, if we look at set B, we should do the same thing, and we'll see that the ones which are shared have already been filled in. So 3 and 7, right? Just 3 and 7, right? They're shared. And 1, 6, and 8 are not. So what are we missing now? Well, the numbers which are in neither of those sets. So we've got our universal set, and we were told that our universal set was all numbers from 0 to 12. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Much faster on paper, I know. Now let's cross out the numbers that are on either of those sets, because if the numbers are in those sets, then I'll not write them here on the outside. If they're not, then I'll have to express them somewhere. So let's see. 1 is here, 0 is nowhere, so 1 is done. Let me just get a different one. So 1 is done. 2 is on set A, 3 is in both, 4 is in neither, 5 is in set A, 6 is in set B, 7 is in both, 8 is in B, 9 is in neither, 10 neither, 11 is in set A, and 12 in neither. So what would be the numbers which are missing? So I've got 0, I've got 4, I've got 9, 10, and 12. So I would have to express those numbers just lying anywhere outside of those circles. So 0, 4, 9, 10, and 12. Again, if we look at the number of elements, what is the number of elements in our universal set? So 3, 6, 9, well, it's 12 plus 1 because we're taking into account 0, so 13. What is the number of elements in set A? Now 1, 2, 3, 4, 5. What is the number of elements in set B? 5 as well. Now, if you notice, in this case, if we add those up, we would have 10. And we still have 5 elements outside, which you could confuse some of you. But those numbers, they will not add up to our universal set because some of those are shared, right? So if I add those numbers, when I add number of elements in A, I'm counting 5, and then when I add number of elements in B, I'm also counting 5. So I'm counting those two twice. So that's why this would give us 10. However, if we actually notice, the number of elements in both A and B would simply be 8, right? And then with the 5 that we have outside, it would add up to the number of elements in our universal set. So there's actually a few names which are interesting. So this in between here, we call this our intersection, right? That's the next thing we're going to cover. But if I asked you what was A, and this means intersection. Oops. Intersection. So basically it means what is in both of them. Alright, so it's a and. It basically means x such that x is an element of A and B at the same time. Alright, let's just, X is an element of B. Alright, so this is what we call intersection, and we should have also union. So the union is what's in either of them. So if it's in any of them, it would be in the union. So X is an element of A, so it's a member of A, or X is an element of B. So if it's in either of those sets, we would have in our union. So let's just see in this example what would be the union and what would be the intersection. So the union of A and B, we would have to get all elements which are in at least one of them. So 1 is in set B, 2 is in set A, 3, so 2, 3, 4 is not, 5, 6, 7, 8, 9 is not, 10 is not, 11, and that's it. What about the union? Well, intersection, just what's in both of them. So that's this, 3 and 7. Just that. And that would be our union and our intersection. This is union. Now, the names, they make sense, right? Union. So you're getting everything which is in at least one of them. If this is you and this is your friend, this is what you have, this is what your friend has. So if you're talking about a union, you two are, I don't know, playing cards together, playing Pokemon cards, I don't know, whatever. You would add all cards that you have with all cards that your friend has, and that's your union, right? Intersection is what you two have in common. So you have a Blastoise and a Charizard, so that's what you two have in common. That's what inside of both sets at the same time. Just a side note, important concept that it's nice for you guys to look at right now is disjoint sets. So when we have two sets and they have nothing in common, so let's say this is my, oh my god, this is my universal set, okay, this is set A, this is my set B. If I have, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Those sets, they would be said to be disjoint, because if we take the intersection, it's empty, right? There's nothing that they have in common, so that's what we call disjoint. If they are non-disjoint, it means that they have elements in common, so they would be overlapping here. You would have, for example, oh my god, right, if this is set A and set B, whatever they have in common here, 1, 2, 3, 4, so the universal set. This is a case, and 5, just to have something outside. This is the case where they have an intersection, right? So if we try to observe, this is our intersection, right? And so A intersection B in this example here would be 1 and 2, therefore they are non-disjoint. Alright, so for our last example here, let's take a look at this problem. So I've got my universal set is all positive integers less than 12. There's a typo here. A is all prime numbers less or equal, okay? A is all prime numbers less or equal than 12, and B all factors of 12. So letter A, list all elements on sets A and B. So let's first list all elements of set A. So positive integers, sorry, prime numbers less or equal than 12. So 2, 3, 5, 7, and 11. That's fairly simple. We've done this before. Now B, factors of 12. So it's basically all numbers that you may have when you multiply and get a 12. If you don't remember how to do this, you may just factorize 12, and then you have 2, 6, 2, 3, 3, 1, 1, right? So 1 is a factor, 2 is a factor, 3 is a factor. If we combine 4 and 4, 2 and 2, we would have 4, so 4 is also a factor. 2 and 3, 6 would also be a factor, and 12. You can combine those in any way, right? So 1, it's just this, 2, 3, 4, 6, and there you go. That's all of them. Now, so we've done letter A. Nice. Now letter B, show the sets A, B, and U in a Venn diagram. So now we have to draw our Venn diagram. So let's draw a rectangle. So it's not going to be a circle, but I'll try to make it good enough. Now this is set A, this is set B, this is our universal set. So let's see, set A, I've got 2, 3, 5, 7, and 11. So, and set B, 1, 2, 3, 4, 6, and 12. So what we have to do first here is try and find what do they have in common, right? So basically what we're doing here is finding the intersection. We don't have to, we're doing that in our minds. And how do we do that? We just look for numbers which are in common here. 2, 3, and that's it. Because any other one will be combining the previous one, so it's not going to be a prime number, right? So the elements that we have inside, which are common to those two, is 2 and 3. Now what do I have on set A, which is not on set B? 5, 7, and 11. What do I have on set B, which is not on set A? 1, 4, 6, and 12. Now the last thing is, what do I have on my set U, which is in neither? So I'm talking about positive integers. So 0 is not going to be there. Okay? Remember, positive integers is our z with a plus. Okay? So since we're talking about positive integers, well, 1 is here. If you find it difficult, you can express the numbers here. So 1, 2, 3, 4. So since it's less and equal than 12, 12 will be an element of our universal set. Now let's cross out what we have already put in any set here. So 1 is in set B, 2 is in both A and B, 3 is in both, 4 is in set B, 5 is in set A, 6 is in set B, 7 is in set A, 8 is in neither, 9, neither, 10, neither, 11 is in set A, and 12 is in set B. So the only numbers that I have left are 8, 9, and 10. And that's fair enough. So I could just spread them around here. So 8, 9, and 10. It doesn't matter where you put it, as long as it's inside of the rectangle and outside of the circles. There you go. So letter B is done. Now letter C. List the elements in the complement of A. So A prime is the complement of A. So this is, what am I missing to get the universal set if I consider my set A? So set A is 2, 3, 5, 7, and 11. So I have to look for the elements which are in my universal set but are not here. So 1, take a look at our universal set. 1 is not in set A, 2 is in set A, 3, 4, 6, 8, 9, 10, and 12. If we look at the number of elements, it would be 7 elements. This is 5, it adds up to 12, so looks fine. Now what about A intersection with B? Well, A intersection B is what they have in common, so 2 and 3. What about A union B is what you add what both of them have. So we're going to have 1, 2, 3, 4, 5, 6, 7, no 8, no 9, no 10, 11, and 12. That would be our union. So, done. What about letter D? So letter D, find number of elements, the number of elements in the intersection between A and B. So we have done intersection of A and B. How many elements do we have here? 2. Now, number of elements in A union B. We've done A union B, so we just have to look for how many elements do we have. 3, 6, 9. And number of elements in the complement of B. So how many elements do I have in complement of B? Well, we haven't done complement of B. So let's do complement of B first. What would be complement of B? So likewise, it's all elements that we need for B to become the universal set. So what do we have in set B? 1, 2, 3, 4, 6, and 12. So universal set is all numbers, all positive integers less equal than 12. So 1 is in B, 2 is in B, 3 is in B, 4, 5 is not, 6 is, 7 is not, 8, 9, and then all numbers up to 11. 12 is there, and that's it. So this is the complement of B, the complement set of B. So number of elements in our B prime, so our complement of B, how many elements do we have here? So 3, 6. Now, we could notice that the number of elements in the universal set should be equal to the number of elements, for example, in set B, plus the number of elements in complement of B. And should be the same thing for a set of A, for a number of elements in set A, and number of elements in complement of set A. Take a look. Number of elements in set B was 6. Number of elements in complement of set B is 6, so that's 12. Number of elements in set A was 5. Number of elements in complement of set A was 7, so that's also 12.